Our second type of domain algebraically is the simplest of rational functions, and we're only going to be talking about polynomials divided by polynomials. Now, we know a polynomial by itself has an unlimited domain, so all real numbers, we can fill in anything into a polynomial. But a fraction, different story. If we have a variable in the denominator, then we have to look at where the denominator is 0 because that would be undefined. That's going to present in the graph either asymptotes or holes. Asymptotes are relatively easy to see. Holes are virtually impossible to see unless you know they're there. So that's where your algebraic domain comes in and is very important. So in our first example, f of x, basically we find out where 3x minus 2 is 0. So I'm going to say, well, it can't be 0. So if I solve, I'll get x can't be 2/3. Now, if I factored the numerator and found a common factor, then that'd be a whole. In this case, we don't have a common factor in the numerator. So I can tell you graphically there's going to be a vertical asymptote at x equal 2/3. Now, I'm going to go ahead and put this in interval notation. Technically, this is your domain. Okay, but all real numbers except 2/3. But I'm going to go ahead and take it a step further, and I'm going to say if we looked at all the x values on the number line, at 2/3, we're going to have this void. So if I wanted to actually look at this from interval notation, we'd be talking about from here to here, and then from here on, like so. So with that in mind, I can say the domain is from negative infinity to 2/3. I'm going to skip 2/3, and then I'm going to go from 2/3 to positive infinity. So I have two different intervals in order to skip that 2/3, and then I'm going to put a union in between, and that is my domain in interval notation. My second example, very simply, is x minus 2 can't be 0. So therefore, x can't be 2. You'll find if you filled in 2 in the numerator, you'd get 0 in the top also, which lets me know if I'd factored that numerator, I'd have a common factor. So graphically, this is actually going to have a hole at 2. It's not going to be a curve. It's going to actually be a line, x plus 2 with a hole. Okay, not worried about that so much right now, but basically that's my domain in its simplest form. Once again, if I put that on the number line, it looks similar to above. So my domain is going to be from negative infinity to 2. I'm going to skip the 2, and I'm going to go from 2 to infinity. So all real numbers except 2. What's different about our third one is that I have two separate denominators. So I know that the 3x, or two separate factors in the denominator. So I know that the 3x plus 1 can't be 0, so x can't be negative 1/3. And I know that 5x minus 4 can't be 0, so x can't be a positive 4/5. So that is my domain in simplest form, all real numbers except negative 1/3 and 4/5. If I put those on a number line, so on the number line I'd put my negative 1/3, I'd put my 4/5, something like that. So this one's going to be a little different in that I have this section over here. I skip over that one, and then that section there. So I actually have three separate intervals. So my domain in blue would be three sections from negative infinity to negative 1/3, union negative 1/3 to 4/5, union 4/5 to infinity. And I'm running out of space there, but you get the idea. And that is domain of the simplest rational functions when it's a polynomial over polynomial.